This screencast is our last topic dealing with equilibrium that we're going to focus on for AP Chemistry, and it deals with the solubility constant for equilibrium, which is Ksp. Alright, so when we've been dealing with weak acids, we have recognized that when we have a very, very, very small K value, that is telling us that very little of the component dissolves in water. We are going to now apply that to when we have a solid that is not typically soluble, meaning it doesn't really dissolve. We are going to look at what it would be, what its K value is, and how much of the product or how much of the solid is actually dissolved. And so the value that we're going to assign to that is called Ksp, and this is based on dissolving compounds. Now, a thing to remember, when we're dealing with K, we have only cared about items that were aqueous, and the unit we used was molarity, pressure, when we had ATM or KPA. Sorry, my pen is being considerably challenging. And now you see a solid. There were different states of substances that you will cancel. We will cancel solids and liquids. These do not contribute to the K value because they're assumed to have no changing value, they stay the same. So anytime that we're doing a Ksp problem and there is a solid in it, which I'm going to guess every single time, you're going to cancel the solid out of the problem and just have, usually you're just going to have the top line, so you're not going to be doing any dissolving. KSPs are listed in Appendix D or given in the problem. You can look them up or you can be asked to use information or solve for it. What we're going to be solving then is how much of the particular solid substance will dissolve in water, and that's what the K value is going to tell us. Here is our sample problem. It says a container of Ag2 at CrO4 at 25 degrees Celsius has reached equilibrium. The concentration of silver is 1.3 times 10 to the negative fourth molar. What is the Ksp value? We have an equation, a silver chromate equilibrium equation, because what's happening at the molecular level is we are constantly forming some ions and constantly reforming the solid. Now, we have a concentration for our Ag, but we do not know what it is for CrO4. We're going to have to do some stoichiometry to solve that. We have 1.3 times 10 to the negative fourth molar, which is the number of moles per liter. We're going to assume that it's 1 liter of Ag. Using my stoichiometry, I see that I have 2 moles of Ag for every 1 mole of the CrO4 minus 2. That would get me an end answer for the concentration of 6.5 times 10 to the negative 5 is our number of moles of the chromate ion. So, to solve our Ksp, we take our products. Well, we don't even need the line. We take our 2 products. We are going to use the 1.3, which is the silver, times 10 to the negative fourth, and because there are 2 of them, I have to square this. And then we're going to multiply that by the 6.5 times, I'm not going to be able to fit that in there, times 10 to the negative fifth, and I'll solve for my Ksp. So I will do the math, and I get a Ksp of 1.1 times 10 to the negative 12th. No unit. 1.1 times 10 to the negative 12th. That value tells me, because it's so small, that I don't have much silver chromate dissolving. In fact, I have very little. So I could comment on how the solubility of silver chromate is very small, and that not much of it becomes ionized. Here's a different sample problem where they give you the Ksp and they tell you it's CaF2 and that it's going to that it will dissolve, And we are going to, they're asking us to find the solubility of CaF2 in grams per liter. Now remember, our molarity is moles per liter, so if we can find moles per liter, we can then do a conversion to grams per liter. So they're just asking you to find the concentration of CaF2. We are starting the problem like we've been doing all along. We are not worried about this solid because it will not appear in our K expression. We have 0 initial calcium and fluorine, and we're going to change by a factor of x, except that over here, because we have a 2, we have 2x. Be aware that you're going to have some crazy coefficients that are going to affect your initial and your equilibrium concentration values. So you're going to see exponents beyond just the x squared that we've experienced a good deal of time in the previous equilibriums. So our Ksp will equal x times 2x, and remember that term has to be squared. Our Ksp was given to us, it's 3.9 times 10 to the negative 11th, and that is going to equal this x, these two products here. We have 2x term squared, so that is 4x squared, because you square both parts, and that ends up giving us 4x cubed when you do the multiplication. When you divide by 4 and do a cube root, your x value is going to end up being 2.1 times 10 to the negative 4th, and that's molarity, which we know is moles per liter. We can take that and we can then convert it to grams per liter when we know that it is, they told us they wanted to know the information about the CaF2. So we have 1 mole on the bottom, and our molar mass of CaF2, if you add it up, is 78.1 grams of CaF2. And the answer ends up being 1.6 times 10 to the negative second. And that's in grams per liter. I'm not sure if I'm going to make it work. There we go. It's squeezed in there. All right, so the problem asked us to find the solubility in grams per liter of calcium fluoride. We found it through a Ksp problem. We found the concentration at equilibrium, and that is the concentration because the stoichiometry says the concentration is for the whole thing, and we were able to then convert it to grams and find the it's basically the solubility. So this is telling us how much will dissolve if you put it into water. You can dissolve 1.6 times 10 to the negative 2 grams in 1 liter.